Hello students, welcome to Sri Chandra's Rank Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 13 of a unit Laws of Motion. So let's begin with today's class. Today we are going to discuss about the circular motion. This is part 2 of the circular motion. Even in the previous class we were discussing about the circular motion. It was the part 1. So let's begin with today's class quickly. Now, what circular motion is all about, we understood. Now, this is the one of the new dimensions of the circular motion. We say that the acceleration of a body moving on a circle of radius r with uniform speed v is the v square by r, and it is directed towards the centers. This people are talking about the centripetal acceleration. We have discussed about the centripetal acceleration in the lecture that has been titled as the centripetal force. According to the second law, the force Fc, it's a centripetal force. This is centripetal force providing this acceleration, and this Fc can be written as mv square by r. This is what we have discussed, and m is the mass of the body, and this force is directed towards the center is called the centripetal force. That we understood. Yes. Now let's understood that for a stone rotated in a circle by a string, the centripetal force is provided by the tension in the string. The centripetal force for the motion of a planet around the sun is the gravitational force on the planet due to the sun, and for a car taking a circular turn on a horizontal road, the centripetal force is the force of friction. Yes, that we have discussed that different agencies are there which provide the centripetal force. Who will provide the centripetal force? This will be can be answered if we know the situation. Yes, and it varies, it differs situation to situation. The circular motion of a car on a flat and banked road given an interesting applications of the laws of motion. So we are going to discuss the circular motion of a car on a level road and banked road. But before we go through this, let's look at few questions and then we will switch over it. It says that a block of mass 2 kg is tied to a string of length 2 meters, something like this. I hope this is a block having a mass of 2 kg and this length of a string, it is of 2 meter. This length of a string is 2 meter, and the other end, this is fixed. The block is moved on a smooth horizontal table. Okay, it is moving horizontally. Let's suppose this is horizontal motion. It has been seen as an vertical, but it is something like this. Yes, and it is going to move like this. The smooth horizontal table with a constant speed of 5 meter per second. What I need to do is I need to find out the tension in the string. So let's rub this. Yes, this is the situation. This is the length 2 meter and the mass of this bob is 2 kg. So what I understood is that in this case required centripetal force is being provided by tension force. Yes, so as tension provides the centripetal force, what I can have, it's a T is equals to m into v square divided by r. The mass is 2 kg, velocity is 5 meter per second. It's a 5 into 5 divided by 2 is the length, and it makes a radius of the circle. It's a 25 Newton. I hope these things are clear. Is it clear? Is it? Great. Ready for the next question? Ready? Let's have a look. What this question is saying, that a block of mass m is kept on the edge of a horizontal turntable of radius r, and which is rotating with constant angular velocity omega about its axis. So it would be something like this: a block of mass m is kept on the edge of a horizontal turntable, something like this. Yes, and this is having friction mu, coefficient of friction, it is mu. Yes, and if coefficient of friction is mu, find the friction between the block and the table. Okay, so it is not being connected, something like this. So this is having mass m, and it has been kept on the edge of a horizontal turntable, and this is radius r. It is not connected, it is just the radius, and it is moving with angular velocity omega. So frictional force between block and the table. So what I need to do is as this is moving on the circular path, this is moving on the circular path, so required centripetal force will be provided by frictional force. And this frictional force F can be given as mv square by r. Yes, look at this. This is, I have compared it with the centripetal force. It's an mv square by r, and as they have not provided v, but they have provided the angular velocity. In the previous class we understood that relation between v and omega, it's a v is equals to r omega. So let's just replace this. It's a m r square omega square divided by r. So this 2 has gone, and that should be m r omega square. So this is the required friction, and this is the friction available. That's why only this block can keep rotating on the horizontal turntable. I hope this is clear. Is it clear? Is it? Are you done with this? Are you? Great. Now let's work for the next question. A very interesting question. That let's assume that a coin is placed on the circular plate at radius r from the center of plate. Now if this plate starts rotating with angular speed omega, find out value of mu. It's a coefficient of friction between coin and plate, so that coin does not slip out. Go through the data one more time and very carefully. What does it say? It says that a coin is placed on the circular plate of radius r from the center of the plate, and if this plate starts rotating with an angular speed of omega, I need to find out a value of a mu between the coin and plate, so that coin does not slip out. So how could you do this? First, do one thing, that have a rough structure of this, have a rough sketch of this, and let's just think that what should I do to make this possible. What should I do? What do you think? How could you do this? What do you think? Let me help you guys. So, have you made this structure? Have you? Have you made this structure? Yes or no? No? Yes? Okay. Let's have a look. That suppose this is the circular plate and this is probably its axis of rotation through which it is rotating with omega, and from here a circular coin is placed. It is placed at a radius r. Yes? Now what you are supposed to do is, what you want is that this is having mass m. Let's write down all the forces. This is mass mg. This is the normal force. Now what do you want? You want that coin does not slip out. So always consider that which forces are there, which will which will make this coin to slip out. Yes, do remember the frictional cases? Yes, we always used to have this kind of thought that whatever the thing that is going to happen, why this is going to happen. Yes, so what I understand is that this force, it's a m omega square r force which will make or which can slip out the coin. So I should apply my friction in the inward direction. So the situation is something like this. This is coin. This is m omega square r. This is friction. This was normal and this was mg. So if my friction is equals to m omega square r, the coin does not slip out. So if I can satisfy this, f is equals to m omega square r, then coin is not going to slip out. Now what is the value of friction? We understand that this f should be less than or equals to mu s into n. In this situation, if I take the maximum value, it would be mu s into mg. Yes, so f should be equals to, this is maximum value. In reality, I should take this as a f should be less than or equals to mu s into mg. Now let's just replace the value of friction, which should be m omega square r. So if I can manage to have m omega square r less than or equals to mu s into mg, or this mm has gone, and if I can arrange mu s should be greater than or equals to omega square into r divided by g. If this can be done, coefficient of static friction is greater than or equals to omega square into r by g, coin does not slip out. This is for sure, that this coin is not going to slip out. This is not going to go anywhere. I hope these things are clear. Is it clear? Is it clear? Is it? Great. So coin is not going anywhere and it does not slip out. Yes? Do you understand this completely? Yes? Interested in doing one more question of same type? Are you? Let's have a look. Let's suppose this is cylindrical vessel is there, and in this cylindrical vessel, let's assume that this is the axis of rotation of the cylindrical vessel. You yourself is standing over here. Yes, you have hold the wall of the cylindrical vessel, and this surface is with friction. This surface is with friction and the coefficient of static friction is mu. So what do you need to find out? You need to find out value of an omega such that you should not fall down. You should not fall down. So start doing it and do it carefully. If you are not about to solve this, you are going to fall down. Yes, so start doing it. What all forces that are acting? Let's have a look. That first force, it must be your mg. It would be your weight. Here you have been connected with this wall. That means the normal force. This way it's an m omega square r, that we understand that this is the centripetal force. So in this case, centripetal force is provided by the normal. And as if you are about to fall out, who will save you? It's a friction force. So this is acting on the upward direction. So the situation is, if I make your free body diagram, it would be something like this. It's an mg, this is friction, this is n, and this is m omega square r. So if I can manage to have F is equals to mg, you will be safe. You will be safe. Yes. Now what is friction? What is friction? It should be F should be less than or equals to mu s into n, and n should be equals to m omega square r. So this is mu s into m omega square r. Is it clear? Now what you need to do is just copy this thing. It's an mg should be less than or equals to mu s into m omega square r. So this omega has gone, and this is equals to omega square should be greater than or equals to g by mu s into r, or omega should be greater than or equals to under root of g by mu s into r. If this could be satisfied, you are not going to fall down. Otherwise you are going to fall down. I hope the things are clear. Is it clear? Is it any doubts on this? Is there anything? No? Great. Let's have a look at this question. What does it say? It says that a hemispherical ball of radius r is rotating about its axis of symmetry, which is kept vertical. This is the axis of symmetry, and around which it is going to rotate with omega. A small ball kept in the ball rotates with the ball without slipping on its surface. This is the ball. If the surface of this ball is smooth and the angle made by the radius through the ball with the vertical is alpha, find the angular speed at which the ball is rotating. Go through the data one more time. If you have a query with this, go with the data. It says this ball is rotating with radius with omega, and it is having a radius capital R. A ball is kept over there, and the surface is smooth. That means no friction is available, and you need to find out the angular speed with which the ball is rotating. So what should I do? Let's have a look. What we are supposed to do is, let's make all the forces that this is the ball having mass m. This would be its mg. Yes, this is the normal force. This is the angle alpha. As it is an alpha, it's an n cos alpha, and that should be is equals to n sine alpha. Yes, this should be is equals to, it's an m r, it's an m into r into omega square r. It's a m r omega square. So this is n cos alpha is equals to mg, that I have written over here, and this n sine alpha is equals to mr omega square. But as I understand that this is the triangle, and this angle is alpha, this is r, this is small r. Yes, this is the angle. So if I make a sine alpha, it's in small r divided by capital R. So small r can be replaced as capital R multiplied by sine alpha. Yes, so let's just replace this, that n sine alpha is equals to mr omega square, and let's replace the r with the help of r sine alpha. So if I put it over here, this sine alpha and sine alpha will be cancelled. So the n is equals to mr omega square. So now let's put the value in the n cos alpha is equals to mg. Mr omega square into cos alpha is equals to mg. This mass and this mass would be the con, and the omega square is equals to g by r cos alpha. While I go for the omega, it's in square root of g divided by r cos alpha. I hope this is clear. Yes, this is very conceptual questions, but when any of the question arises, this kind of questions, any would be there. Yes, we need to stick to the basics, that write down all the forces that make your particle in equilibrium, and then go with the balancing, or that means the balancing of the forces. I hope this is clear. Okay, great. Now we are working for the motion of an object, on circular road. Basically we are going to discuss two segments of this theory. Yes, one is the level road and another is the banked road. When I say we are about to discuss this on the level road, that means let's suppose this is this circular path and you are going to traveling on this, approximately on this, and while you are talking about the banked road, a situation would be something like this. This is your reference horizontal level, and from this road would be something like this. This is theta. Again, one more thing, this theta is very small. This could not go to the 10 degree, 20 degree, 30 degree or something. No, it is not that. But this is very small, but it is having a larger effect when we bank the road. How this effect will play a role, that we will see in the theory sections. So let's have a look. Let's begin with the level road. So first we are going to discuss about the motion of a car on level road. So let's suppose this is the car and this is the level road. I have directly shown this segment only. Yes, this car is there, mass m, that means the weight, it's an mg, the normal force is do acting, it's an n, and the friction would be acting on the inward direction. So now as there is no acceleration in the vertical direction, we can write n is equals to mg. Yes, this force n, this force mg, and no acceleration in vertical direction. So vertically it's an n equals to mg. Next, the centripetal force required for circular motion is along the surface of the road, and it is provided by the component of the contact force between the road and the car tires along the surface. This is by definition it's in frictional force. Yes, so that's why we are going to have a frictional force as the centripetal force in this situation. Note that it is the static friction that provides the centripetal acceleration, and static friction opposes the impending motion of the car moving away from the circle. So it is the force which helps us, so that my car is not going to be move away from the circle. Yes, so now if I put all the relations, then I can have it's an F is equals to mu s into n, and what I can have is the F is equals to mv square by r. So if I put the value that F should be less than or equals to mu s into n. Yes, so it's a mu s into n should be equals to mv square by r, and n would be the mg. So if I derive for it for the v square, let's have a look at this. It's a v square should be greater than or equals to mu s rn by m, and if I replace this n with the mg, then I can have it's a mu s into R into G. Now, one very interesting fact is that this is independent of the mass of the car. That means that whatever could be the mass of the car, this speed is fixed enough. Yes, so you cannot have the argument that hatchback should travel from this, or sedan should travel from this, or a super sedan should travel from this. This is the fix for each car on the level road. Yes, this shows that for a given value of mu s and r, there is a maximum speed of the circular motion of the car possible is, it's a Vmax is equals to root of mu s into rg. If your speed exceeds this, if your speeds exceeds this, you are going to throw away from the circular path. Why? Because as soon as your mv square by r increasing, if your mv square by r increasing, f is the fix because it is a mu s into n, as, and that would be equals to mu s into mg only. Yes, so as at certain situation f is not able to control this mv square by r, and in that situation your car will be moving out of the circular path. So this is what happens when we see the certain accidents where a circular path were there and certain cars or certain objects have been moved out of the trajectory. Yes, this was the situation. So this is the maximum safe speed on the level road, and that could be given as under root of mu s into rg. Let's have a one numerical on this. It says that find the maximum speed at which car can turn round a curve of 30-meter radius. R is given. On a level road, if the coefficient of friction between the tires and the road, it's a mu, it's a 0.4, and acceleration due to gravity g is given, which should be at 10 meter per second square. So now you can have, it's a Vmax should be equals to root of mu s into r into g. This mu s, it's a 0.4, it's a 4 by 10 multiplied by radius, it's a 30 into g, it's a 10. So this 10 has gone, and this is of root of 120 meter per second. Yes, this is the maximum possible safe speed that can be used while driving on this level road. I hope this is clear. Yes, great. Now let's move to the motion of a car on banked road. So before we proceed, let's just have a look to the situation. A situation would be something like this. This is the level banked road, sorry. This is theta, and let's say this is your car. This is m. So let's just write out all the forces that is acting. This would be the mg. This would be mg cos theta. This would be the mg sin theta. This is normal. As this is theta, even this should be theta. That means it is the n cos theta, and this would be n sin theta. I hope this is clear. Yes, a friction would be there. Which is in the downward direction. So even in this situation, friction would be acting on this, and if friction is acting on this, that means there is a force which is F cos theta in this direction, and there is a force F sin theta in this direction on this same line or on the parallel to the n cos theta. I hope this all things are clear. Is it clear? So let's just write down the relation that we understood, that this n cos theta, yes, this is, so as this is the friction as this is the friction, what I need to do is I made a mistake, that F sine theta should be on this direction. Oh, that this is the friction in the downward direction. So F sine theta should be in this direction, because this is the direction of friction. This is the friction. Yes, correct. So let's just write down the relation that n cos theta is equals to mg plus f sine theta, and n sine theta plus f cos theta, that should be is equals to on this side. On this side, this would be the mv square by r. Yes, but we understood that f should be less than or equals to mu s into n. So if I understood that if F frictional force is less than or equals to mu s into n, we need to find out the Vmax. That means by putting the F is equals to mu s into n, we using relation 3 and 4, we can have n cos theta is equals to mg plus F was there, so I have replaced this with the mu s into n sine theta, and n sine theta plus mu s into n cos theta should be equals to mv square by r. So if I replace this with the value of phi, what I can have is the n is equals to mg divided by cos theta minus of mu s sine theta. And if this was the case, what I can have is the mg into sine theta plus mu s cos theta upon cos theta minus mu s sine theta should be equals to mv square max by r. This m and this m would be the gone, and this could be written as Vmax. Vmax is equals to Rg into bracket mu s plus tan theta upon 1 minus mu s tan theta. But if it's a Vmax, it would be a square root of this. So comparing this equation with the equation 2, we see that the maximum possible speed of a car on a banked road is greater than that on a flat road. On the flat road or on the level road, it was under root of mu s into Rg. Yes, this speed is greater than this, and that is the reason we used to have a banked road. Now let's have one more application or one more relation with this. Our Vmax was root of R into G into bracket mu s plus tan theta upon 1 minus mu s tan theta. Yes, this was the Vmax. Now if I want to derive this for V minimum, then only direction of friction changes, and rest of the things will be the same. So V mean could be written as, what I need to do, I need to replace this mu with the minus of mu. So V mean could be written as, it would be under root of Rg into bracket tan theta minus of mu s divided by 1 plus mu s tan theta. This is the V minimum. Yes, I'm just replacing mu s with minus of mu s. I hope this is clear. Is it clear? Is it great? One more thing. If we need to remove dependency on mu, what was Vmax? The Vmax was root of Rg into bracket mu s plus tan theta upon 1 minus mu s into tan theta. Yes, what mu s is, what mu s is, we say it is the coefficient of static friction. Yes, now what parameters will provide the mu s? Then we will say a certain components of n cos theta and all that stuff will provide the mu s. But if I want that dependency on the mu s should be removed, what would be the Vmax? Let's have a look. So if I put mu s is equals to 0, then the velocity could be written as, that is, r into g. This mu s is 0, so multiplied by tan theta upon 1 minus 0. It's a 0. It's a 1, sorry. So this is the optimum speed, V optimum, that we call as, this is V optimum should be is equals to root of, V optimum should be written as root of Rg into tan theta. Yes, this is the speed. This is the speed where wear and tear due to friction will be minimum. I hope this is clear. Yes, this is the speed where wear and tear due to friction will be minimum. Is it clear? Is it clear? Any doubts? No? Okay. So we have basically three relations. One is the Vmax, one is the V optimum, and another that we have derived for the V minimum. I'm sure that you will able to solve the questions that are just the data feeding kind of questions. Yes, that R is given, G is given, theta is given, mu is given, everything is given, and you need to just calculate it. Yes, so I'm sure you can do this. And we are going to switch to the one more concept of the circular motion. It's a conical pendulum. Now what is it? What a conical pendulum is? That what we are going to see is that, let's suppose this is the pendulum and that has been tied with this string, with the help of string, to a rigid support, and this is going to move in this path. Yes, it's in horizontal circle. Yes, it's in horizontal circle, and this is going to move. This is going to be rotated in the horizontal circle. So let's assume that this is mass m, and when this is mass m, this is the mg, this is the tension T. If this is tension T, this could be written as T cos theta, this could be written as T sin theta, and this is the mv square by r, or you can have with the mr omega square. Let's work with the mv square by r. So if I write down all the forces that are in vertical direction, I can have, it's a T cos theta should be equals to mg, and it's a T sin theta that should be is equals to mv square divided by r. This is relation number 1. This is relation number 2. Let's divide 2 by the 1. It's a sin, this tt would gone, and sin theta by cos theta, it's a tan theta, that should be is equals to v square by r into g. This is the tan theta, this is the angle theta. Tan theta is equals to v square by rg, and from this you can have that v square is equals to r into g into tan theta. But this r is the radius. If I want to replace it, with the help of length of the string, what I can do is that, as I can see this triangle, this is the 90 degree. So if I write sin theta, that would be equals to r by l. So if I want to replace r, it's an capital L sin theta. So let's just replace this, that v square is equals to r into g into tan theta were there, and I was replacing with L into sin theta multiplied by g multiplied by tan theta. What is tan theta? It's a sine theta by cos theta. This is v square. So that should be is equals to g into L multiplied by sine square theta divided by cos theta. This is the v square. I hope this is clear. Is it clear? Is it any doubts in this? Any doubts? Is there anything? Any doubts in this? Anything? No? Great. So this is v square. This is v square. Now, if I want to replace it with the omega, if I want to replace it with omega, I can replace this with the help of v is equals to small r into omega. Yes. So for this I need to take this relation, that r square omega square is equals to r into g into tan theta, and this r and this r, that means one of the power would be gone, and this omega square could be written as g tan theta divided by r, while r is the L sin theta that we have derived. So L sin theta, that could be written as g sin theta by cos theta into 1 by L sin theta. This has been gone, and this could be written as g by L cos theta. This is omega square. This is omega square. And if you wish, you can have a time period also from this relation. Let's have a look. That omega square could be written as g by L cos theta. This is 4 pi square by t square is equals to g by L cos theta. So t square should be is equals to 4 pi square into L cos theta by g. So this is t is equals to 2 pi root of L cos theta by g. This is the time period. This is the time period. This is t is equals to 2 pi root of L cos theta by g. This is the time period. I hope this is clear. If they want the frequency, then this could be written as 1 by 2 pi root of g by L cos theta. I hope these things are clear. Is it clear? Is it? Are you sure? Yes. So while I discuss this, I do understand that the time period of this pendulum t is equals to 2 pi root of, it's an L cos theta by g, t is equals to 2 pi root of L cos theta by g. So this time period depends on L, it's the length of the pendulum, and it depends on the cos theta, because mostly the g is fixed, 2 pi is always fixed. Yes. So this is the dependency of the time period of the conical pendulum. I hope this is clear. And what about the velocity? The dependency of the velocity. Have you remembered the formula for the velocity? Have you? Did you? It's a v square is equals to rg tan theta. This was v square equals to r into g into tan theta. Yes, again this r is the radius of that circle, and this is the formula for the velocity. So let's have one of the question. This is the vertical, this is the theta, this is the theta, and this theta is of 30 degree. This is the pendulum, this is 45 degree. Find out ratio of time period 1 is to time period 2. This is the first, this is the second. So what I understand is that it is directly proportional to, time period is directly proportional to the root of cos theta, and if it is directly proportional to the root of cos theta, this is t1 is to t2 is equals to root of cos theta 1 is to cos theta 2. That would be, this is cos 30 degree divided by cos of 45 degree. Cos 30, it's a root 3 by 2. Cos 30, yes, it's a root 3 by 2, and cos 45, it's a 1 by root 2. I hope these things are clear, and this would be the answer. You got it. I hope these things are clear. Is it? Yes? Great. Any issue, as any concern with this? No? Well done. So let's just wind it up this session over here. Yes, this is all about the circular motion. We have discussed 2 lectures of the circular motion, part 1, part 2. Yes, go through this carefully, and you will be done with the circular motions. Yes, next we are going to discuss the vertical circle in the next unit, work power energy. Yes, so we are just on the completion of this laws of motion. Yes, so please revise it thoroughly. Do as many questions as possible, because this is, as I said in the very first lecture of this unit, that this is the heart of the physics, and to get command over this, we need to practice a really hard. We need to practice a really hard. Then only we can have a very good command over it. So please do as many questions as possible, because only questions can save us. Thank you. Have a good day. Take care. Bye bye.